Now let us discuss some properties of equipotential surfaces. Properties of equipotential surfaces, and this is very important from the point of view that this connects the electric lines of forces with the equipotential surfaces. So now let us recall that for a point charge, if it is positive charge, then the electric lines of forces emerge out from the point charge towards infinity. And the equipotential surfaces around this point charge are spheres S1, S2. So now it is evident from the diagram. Now again we draw the equipotential surfaces for a line charge. This is a point charge, line charge. So the equipotential surfaces are cylindrical surfaces. Let us take another cylindrical surface. So these are the two cylindrical surfaces, S1 and S2. And recall that the electric lines of forces are radially outward. Again, for plane sheet of charge, this is the plane sheet. The electric lines of forces are perpendicular to the conductor, both sides. We are considering here positive charge only. Now the equipotential surfaces for this sheet are planes parallel to the conductor sheet. This is S1, S2 on either side. There are several equipotential surfaces. So from these three diagrams, it is clear that the electric lines of forces are always normal to the equipotential surfaces. So the first property is electric field lines are always normal, or in case of plane sheet, perpendicular to the equipotential surfaces. In case of curved surfaces, we use the term normal. In case of plane surfaces, we use the term perpendicular. We can also use the term normal. This is more general term. So this is the property number one. The electric lines of forces are always normal to the, here a line normal to the sphere is radially outward, radius vectors. A line normal to the cylindrical surface are radially outward lines. These are the perpendicular lines. So this is the first property, very important. Second is related to the work done. Now potential difference delta V is nothing but the work done in carrying a charge from test charge from or charge from one point to another point. Suppose these two points are A and B. So we write it as VB minus VA is equal to W upon Q test charge. Suppose test charge is taken. Now we are taking the test charge from this surface S1 to this surface S2. So here is point A, there is point B. So VB minus VA is nothing but the work done in taking the charge from A to B divided by the test charge, because test charge is taken from A to B. Source charge is Q. So now if these are the 2 points on the different surfaces, then this is the definition. Also this definition holds if we take 2 points here on the same surface. This is point A, this is point B now. So now from the diagram, VA is equal to VB because both the points lie on the same surfaces. Let the potential at here is V2 because potential on this surface is V1. Let all points have equal potential on this surface. All points have equal potential on this surface S2. Let it is V2. So VA and VB both are V2 here. VA and VB are both V2 here. So let us put the value VA is equal to VB is equal to V2 in this expression. So we have 0 because VA is equal to VB. 0 is equal to W upon test charge, and this concludes that W is equal to 0. This is very, very important. That is, no work is done in moving a test charge or here a charge from one point to another point of electric equipotential surface. This is very, very important. No work is done in moving a charge from one point to another point of the equipotential surface. So this is property 2. The third property is, now here we have seen that if the potentials are different, V1 and V2, V1 and V2, V1 and V2, or we take another here V3. So if potentials are different, then the surfaces are also different. So there is no question that the two equipotential surfaces ever cross each other. So no two equipotential surfaces can intersect each other. So these are the three basic properties of equipotential surfaces.